We'll now talk about signal and noise in fMRI to better understand how we can analyze signal, how we can improve signal and decrease noise when we talk about functional magnetic resonance imaging. So what is signal? One way to think about signal when we look at this anatomical image here is to consider different intensities that are sort of reconstructed here on this image in the form of numerical values that are underlying these different gray shades that we're seeing here. And in this T1 image, a large signal is indicated by higher numbers as well as by lighter colors, lighter sort of gray shades, whereas a small signal is indicated by lower numbers and black. So this image here, which is a T1 image of an anatomical image of the brain, allows us to distinguish between different tissue types. So signal in this case is the ability to identify different tissue types, such as cerebrospinal fluid here shown in gray versus gray matter shown here, for instance, in the caudate nucleus versus white matter shown here in the in this fiber tract. When we talk about functional MRI, then signal really is considered the change in the bold signal, in the signal magnitude across time. So we're more interested in how each voxel changes its signal intensity given the regional cerebral blood flow across time, and ideally this correlates with the task that we ask our subjects to perform. So signal is the change in bold intensity that is specifically related to our experimental manipulation when it comes to functional MRI. So we have the anatomical MRI signal on the left and the functional MRI signal here on the right. And the way we then analyze this, and just to briefly illustrate this, we know exactly what happens in the experiment, and we can identify the time points at which, let's say, our participant is paying attention to a certain task within the experiment. And we can sort of idealize this via these boxcar regressors that we then create. So in the red, you see sort of the timeline of the experiment, how long something was on that the participant was doing or attending to, versus off when the subject was doing nothing. And we would then expect the signal of a region that is involved in this task to follow at least approximately the timeline of the experiment. We know a little bit more about this. We know what the canonical bold response looks like, or the hemodynamic response function here. We know that it takes a little bit of time to rise in about 5 seconds to threshold, and then it takes a little bit more time, maybe another 5 seconds to go back to baseline after sort of a dip that occurs here. And we can use this also and combine this with our signal. So let's consider an example to illustrate how difficult it is to identify the bold signal. So let's consider someone being at rest versus someone squeezing one's hand. And this is one of the type of experiment that triggers one of the largest bold signals in the human brain. So what type of signal occurs? And we can look at this at these images. So this is someone being at rest in image A, and this is someone squeezing their hand. And there's a huge bold signal difference, especially here in the motor region. But you can clearly see that we cannot identify this just with the naked eye. So this means we need to have some statistical techniques to be able to identify this. So just as a reminder, this is the rest image, this is the active image. And the location we're looking at are here in the motor cortex, namely specifically the hand region. And again, this is one of the regions that gives us the highest amount of signal change when someone is performing this task, when someone is squeezing the hand. And it's often used as a sort of quality control. If you have any kind of motor movement in your experiment, then you can identify the time point that someone is moving the hands or pushing a button, which is a sort of low-level hand movement. And you can check whether you get the correct hemisphere. So if someone is pushing with their right hand, you would want to see this, to see the activation in the left hemisphere at the specific time point within the experiment. So it's kind of like a control on whether you are creating the right regressors with the right timing, because that is, again, one of the largest signal changes that we observe in fMRI. However, when we look at cognitive or affective tasks, signal changes are typically much smaller, in the order of 0.5 to 1%, and even smaller when it comes to stimuli that are more complex, such as, let's say, economic stimuli, and we're looking at the change across time in economic variables and their correlation with the bolt signal. So we're talking about tiny signal changes here. But at the same time, we're talking about a lot of noise that we have to deal with. So this is showing the difference between these two images here. And you can see that, in fact, if you subtract one image from the other, so if you subtract the rest image from the active image, you can see that the hand region actually does respond. Right? This is about in motor cortex, and it seems to have bilateral effects. But when you then look at signal change, so this is the same image but calculated as percent signal change, then you see still desactivations in this region, but you can also see the amount of noise that is present, for instance, outside of the brain. Now we know what's inside and outside of the brain, so we can identify this as clearly being noise, and you can remove this from your analysis. But the illustration that the point that this image makes is there's a lot of noise, and the noise is as large or larger than the signal that we're getting. So how do we distinguish signal from noise? So we've seen now that there's a lot of noise and very little signal when it comes to the bolt signal. The bolt signal change is very small when we look at task-related brain activity, especially compared to the total intensity of the MR signal. And the noise around it is also relatively large. How bad is this really? Well, if you look at this image here, it might give you a good impression of how bad this is. So there's actually more signal change around the brain than in the brain, whereas you can still identify the hand areas here. But this really depends on how large task-related activity is relative to the total variability. And the total variability obviously includes these sources of noise. We have these various sources of noise, obvious ones such as head motion, which have a large effect, obviously, on specific areas of the brain, especially the edges of the brain. But then we also have physiological noise and thermal noise that contribute to the signal in ways that we don't want it to. Heart rate and respiration actually can be related to the task. So first of all, they cause changes in blood flow within the brain, and therefore also changes that we observe in the bolt signal. If you have an increased heart rate, obviously you have a higher blood flow, and respiration also leads to differences. Can lead to differences in the bolt signal, and these can be related to the task. For instance, if the subject is more aroused, these two increase. The scanner temperature and the subject's temperature cause thermal noise, which also changes and affects the MR signal, especially the bolt signal that we're interested in. And that is something we will see in the images. But the good thing about this is that thermal noise typically is unrelated to the task and therefore random. And this is something we can take care of via signal averaging, as you'll see in a moment. There are other sources of noise that we won't discuss here, but the average, the idea here is that there are many sources of noise that impact our signal, and therefore the total variability of the bolt signal that we're looking at. So we're increasing total variability via all of these different sources of noise, but it does not affect task-related activity. which makes our job harder. Now, we talk about 3 different measures of signal quality or signal magnitude in the scanner. The first one is called the contrast to noise ratio, and that relates only to structural images like the ones I'm showing here. So T1 and T2. And it's basically the intensity difference between 2 types of tissues. So in the T1 image, you want to maximize the difference between fluid and white matter, fluid being shown in black here, white matter being shown in white. And this allows you to identify these different tissue types. In the T2 image, this is reversed a little bit. Fluid becomes white, so you identify the difference between fluid and other parts of the brain. Whereas in the T1 image, you can also identify gray matter. And this depends on this T1 or T2 contrast. Both are different, where we have different times where the hydrogen atoms relax back to or align back with the magnetic field. So the magnetization increases at different speeds for these 2 tissue types, which allows us or gives us this contrast. We are mostly interested in signal to noise ratio and functional images when it comes to experiments and functional MRI. And here we're talking about the strength of the signal relative to the sources of noise, where the signal, in fact, is the amount of the response of a given voxel to our task manipulations. So we're really looking at how much does a given voxel respond to the experimental manipulation that we are interested in. That is signal, whereas noise, again, refers to all of these other sources that we talked about. Random variation that is unrelated to the experiment. So functional SNR reflects how a voxel reacts to the experimental treatment, and this is relative to other sources of noise. Finally, we have raw SNR, which is something that's assessed by physicists at the scanner site using phantoms. So we have these types of phantoms. At the beginning of the day, the physicist or MR technician places these inside the scanner. And then raw SNR is simply the ratio of the intensity within the sample. So this phantom here or this phantom here relative to the intensity outside of the sample, and this is used commonly for quality assurance. So it's a rough way to assess how well the scanner is doing on a given day, and if it's doing badly, maybe identify problems and correct those before we start investing or putting subjects in there, right? Going back to the problem, so we do have low signal to noise ratio in fMRI, again illustrated by this image here. But there's a way to get around this, luckily. And the solution for this is borrowed from electroencephalography, an older method. Namely, we use signal averaging, such as is done in ERPs. They're called event-related potentials, where you time lock the response, the neural response, the response that you're measuring with your method to periods of interest in the task. Those periods of interest include the time point when, for instance, you show a decision to the participant or you show a stimulus to the participant and you're interested in how the brain responds to this stimulus or to this task. So we're time blocking. Then we're repeating the same event over and over again in the experiment. Let's say 30, 40, 50 times. So you're doing the same thing within the same conditions over and over again. This allows us to then time lock and average, right? So we have a response, I'll show this to you in a second, that is specific for a given trial. There will be random noise around it, around the signal that we're interested in. But when the noise is random, averaging across different instantiations of the same event, which should lead to similar neural responses every time we do the same task. We should average out the noise, but leave the signal intact. So let me show this how averaging or time-locked averaging works. This is an fMRI experiment from, I believe, the 90s, where the researchers were interested in visual responses to these types of checkerboards here. So these checkerboards, they maximally drive neural responses in early visual cortex. And what they did there is they had a set of, let's say, 150-ish trials for each subject, and then they drew from this set of trials. So each set of trial is time locked to the beginning when you start showing this checkerboard until when you stop showing this checkerboard. And then afterwards, this is followed by just a blank screen where the subject can rest a little bit. And then you draw from this, and you see that and average this. So if you have just one trial, you can see it's very noisy. You cannot really identify a response, only if you try it really hard. At 4 trials already, you can see that for at least for subject 1, but not for subject 2 so much. So it depends on the subject a little bit and the variability of their neural responses to the stimuli. But you can see that there is something emerging. 9 trials, still better. 16 trials, we now have somewhat of a hemodynamic response with some really large outliers around it here. Remember, the method is we have a whole sample of 150 trials, and we're randomly drawing from this sample with replacement to make these averages, right? So here we drew 16 trials from 150 trials, did this a number of times, let's say 40 times, and then plotted these on top of each other. So each average here is based on 16 trials, but a random set of 16 trials from a larger set of 150 trials. So we keep going and doing this. We increase the number of trials that we average over, and you can see that more and more of a signal is emerging for both subjects now, such that when we have 36 trials, we're actually quite optimal here, right? So we have not much changes when you go to 64, although when you look at this graph here, the standard deviation still seems to decrease until up about 45, 60 trials, at which point the differences across the averages decreases, right? No longer decreases. So at 36 trials, it looks like we're about optimal. So we should repeat each trial in the fMRI experiment about 36 times to get a good resolution bolt response with little variability. So once we start averaging across trials, we can actually get a good representation of the bolt response that to the stimulus that we're interested in. So let's have a quick look at how signal averaging works. So in the top panel here, we have an fMRI time series. You can see that there are some colored parts, and they are reflective of time points that we're interested in. So when a subject sees a particular stimulus, let's say a face, or when a subject makes a particular decision, let's say a trust game decision. And so we want to know what the bolt response is during these time points. Then the first thing that we do is we time lock these time points to the start of the onset of the decision. So this is when we show the subject the decision screen, now make a trust decision, right? Do you want to trust this other partner? And then we look at over a period of 20 seconds, how does the bolt response look like? So we have these individual time points. This is the start of the decision period, and this is the end of the decision period shown in color here. Start, end, start, end. In black, the subject is basically resting. Those are periods between the trials when the subject is not doing anything and just preparing for the next decision. You can see the individual responses to the decisions shown here in the different colors again. So we have green shown back here. So there is a bit of a rise and then a bit of a decline. And we see this for every single time point in the experiment. Now we can't tell much from this, right? This is pretty messy looking because of the effect of random noise affecting each time point differently. But when we average across this, now with the onset time of all of these aligned, right? So we're aligning the onset of the decision period for each of these different trials here with each of these different bolt responses that we're getting. then we get an average bolt response that kind of makes sense. So it's we have this rise to threshold. The peak is about where we would expect it from the bolt response, and then a decline with a little bit of an additional rise at the end. But the important thing are the first 12 seconds here. And this is basically how selective averaging works. This is the same approach that is used in electroencephalography or ERPs, event-related potentials. So again, let's go over this really briefly. This is the time series of the entire experiment. We have 400 time points or more, but we're interested in time locking each of these responses to the event that we're interested in. So that is the 0 time point here. And then we're looking at a 20-second period after the stimulus came on the screen, after the subject started deciding. Then we're getting this kind of messy array of bolt responses to the stimulus. But when we average them, we get a hemodynamic response that makes sense.